Hello everybody and welcome to this video where we're going to be talking about a denoising algorithm. Alright, so by denoising we mean that we get rid of the noisy pixels within an image. So I have started with this slide over here where we remove the noise from this noisy image and restore back the original image. Alright, so the algorithm we have over here is for the salt and pepper noise. Okay, and usually the salt and pepper noise are always just 0 and 1. I mean 0 and 255. There's nothing in between, nothing gray in it. Okay, so it's easier to detect. All right, so let's look at the core of this algorithm. This algorithm works by minimizing this summation function over here. So in the end of this video, we're going to have a fully working Matlab code, which you also can play with, and it will do, the genuine denoising of the algorithm. So this function over here is actually very simple, yet it's very, very powerful. I was actually surprised to see it restored the image from 90% noise. And I will show you that right now in the video, and you'll also have the code in order for you to play with it if you would like to. Right, so this summation looks scary, but it's actually very simple. All right, now this represents a function which we choose. Okay, let me show you this function if I can. It's really, really quick. This is the function which we have chosen, and this function is chosen particularly to conserve the edges in the image. Right, so this is the function that we see over here. Now, where are the variables in this optimization function or minimization function? This Vij represents the variables in this summation, which are every detected noisy pixel within the image, or at least the window on which we are working within that image. Sometimes we don't want to work on the whole image all at once. We want to work on a smaller window within that image. This can really lead to much faster calculations. Okay, in my experience, it did not really affect the quality so much. Okay, but it affected the speed of the calculation. Working on smaller windows within the image has resulted in a faster calculation time. All right, so let's wrap up with this ugly, summation function over here. So again, this represents the noisy pixel. So every noisy pixel that is detected according to a specific criteria that we're going to talk about right now, hopefully in this video. So every noisy pixel that is detected within an image or the window on which we are working is represented by a variable within this summation over here. Okay. So what about this other term over here? This represents a neighbor for the noisy pixel. So every noisy pixel has got 4 neighbors: the pixel above it, and the pixel below it, and the pixel to the right, and the pixel to the left. Okay, so we have 2 summations over here. Now those 2 summations over here, whenever we're gonna code them in Matlab, each one of them is represented by a for loop. The first for loop is for every noisy pixel. Okay, for every, so the first summation, will be for every noisy pixel. The other summation over here for every neighbor of every noisy pixel. Okay, so it might look scary, but it's not actually that much scary. Now, we have 2 cases. The neighbor of the noisy pixel could be a non-noisy pixel. Okay, in this case, it will be constant. It's not going to change throughout the iterations of the minimization. Okay. The other case, okay, is when, if you look over here, okay, is when the neighbor belongs, okay, or intersects with the noisy pixel set. Okay, in this case, you need to pay attention because this noisy pixel, this value over here is not going to be constant. okay? And it's going to be variable as well, okay? So you're going to have to pay attention to this, okay? And it will be a noisy pixel. So it's going to be a variable that represents a noisy pixel, okay? So in the case where we have the noisy pixel, or the neighbor of the noisy pixel is not a noisy pixel, it will belong to this summation, okay? And in the case where the neighbor is a noisy pixel, it will be covered by this summation over here and multiplied by a half, okay? So we will, by whatever method you want, okay, in our case we will use the conjugate gradient method, okay, it worked very nicely. We will minimize this function by continuously changing the variable of the noisy pixels, okay, until we reach the minimum value for this whole entire summation over here. And frankly, this minimization process worked wonders. It really restored the images just like I showed you in the beginning of the video. And it did a very, very fantastic job. Now, before I wrap up and move to the Matlab code to show it to you really, really quick, I just wanted to just try make sense out of this summation over here. Now, the noisy pixels usually are straight out in this case, in this type of noise, the pepper and salt noise. It's straight black or straight white, and it's usually very far away in value from the surrounding pixels, okay? So if I, throw a noise in this, part, in this, space over here, it will look so much different from the surrounding pixels, and it will look so much odd and different and away. So if you look at this summation, it looks complicated, but it makes a lot of sense and a lot of simplicity, because you're just trying to minimize the difference between the noisy pixels and its neighbors. That's it. If you find the solution where each noisy pixel in the surrounding noisy pixels has got the least difference with its surrounding pixels, that does not look so odd, then probably you have, reached the best value possible. Okay, but if the pixel looks so much odd and so much different from the surrounding pixels, this is the situation where it will look like noise, right? So this is the trick. So, this summation looks so much complicated, but it's actually simple. All right, so how do we detect a noisy pixel? So right now, this is kind of like the diagram. We have the noisy image, and sometimes we don't want to work on the whole image all at once. So we extract a window from the image and work on it separately, and then go to the next window and the next one and the next one. As I said before, that in my experience, it did not really result or affect the quality so much, but it resulted in a faster calculation time. Okay, whenever on kind of like smaller windows within the image rather than the whole image all at once. All right, so how do we recognize or detect? So right now, the next step, we're going to have to identify the noisy pixels. So how do we identify the noisy pixels? In our algorithm over here, we have two conditions. The pixel either have to be 0 or 255. Okay, because as I said before, the pepper noise is only straight out black or straight out white. So this kind of like makes our work much easier. Okay, now the other condition which should be satisfied as well, you're going to have to use AND, is that the noisy pixel or this pixel does not equal the median of that pixel. Okay, now this median is calculated using the adaptive median filter. You can look that out. I'm not going to get into it right now. Okay, but the adaptive median filter changes the window size according to some certain conditions. Okay, and be careful about the value of the minimum and the maximum window size because it will affect the performance. Until I got those values right, the algorithm did not work properly. Okay, because if you use a very small value for the window, whenever you calculate the median, you're not going to be able to detect all the noisy pixels within the image. Okay. All right. So that was kind of like technical. So after you detect the noisy pixels, you just use whatever method that suits you to minimize that summation function, as I've told you before. So right now, let's jump into Matlab and have a look at our code over here. First, we read the image, right? All right, and now we're gonna have to add some noise, some pepper noise to the image. In my case, I've added 0.8, which is very, very high actually. All right, guys. So I want to give you a quick run in the code over here. First of all, okay, I will provide the link to my GitHub in order for you to play with this code, okay, if you want to. All right, so my code consists of those files, so please place them in the current directory along with the image that you want to denoise as well. So in case you want to work on a different image, just change, the name in this link over here where you read the image to work on. So before I do anything, let's just run the code to give you an idea of how this code works. All right, okay, until it finishes, it will just take less than a minute right now to finish the calculation. So over here, we have the main file, which is, the main code. We also have the conjugate gradient method, which is the minimization algorithm, which we use to minimize the summation function. Okay, and we also have the summation, okay, function, which I've explained before. And we have also the gradient, which calculates the gradient numerically. Why do we calculate the gradient? Because we need it for the conjugate gradient method over here. So we got the result over here. It took about 18 seconds, which is not bad. All right, I have noised this image up to 80%, okay, with the pepper noise. Let me show you the noised image over here. Okay, so we have added all this noise to the image, and yet, as I told you before, it's a very powerful algorithm. It has restored this noisy image with 80% noise into this one, which is very, very powerful for this simple summation. All right, so I'm really impressed by this image. Even if you add up to 90% noise, it will also restore the image back. So it's a very, very nice, powerful. It's a very, very nice, powerful algorithm actually. All right, guys. So now that you have seen the code in action, it's a very powerful one, at least for the pepper noise. All right, I want to give you a very, very quick round, just the main headlines, okay, in the code for those who are interested in the coding process. So first of all, we have this big for loop over here because you might want to process the image multiple times, okay? But in my case, it did not make a big difference. I just process the image once, okay? Sometimes you just want to bring the image and do the same process for that image multiple times. All right. Now, I have two for loops over here that jumps between the rows and the columns because I don't want to work on the whole image all at once. I want to work on smaller windows within the image. So those two for loops create the window effect, okay, over here, okay? So this is something. So once we got the window, we will calculate the adaptive median filter for that window, okay, throughout this code over here. So why do we need to find the adaptive median filter? Because we want to detect the noise based on the comparison with the adaptive median filter values of that image, okay? So we have found the adaptive median filter of that window or the image, okay? Let's move to the next part, which is the noise identification part over here. So those two for loops are for the noise identification part. Those are the two conditions which should be satisfied for a noisy pixel to be considered a noisy pixel, which is the noisy pixel should either equal 0 or 255, and at the same time the noisy pixel should not equal the value of the median, adaptive median pixel, okay, at that pixel. All right. So if those two conditions are satisfied, then that particular pixel is added to the noisy set, which we will work on. Okay. So now the next step over here is to put those noisy pixels in a vector and then send it for the conjugate gradient method, conjugate gradient optimization method, in order to find the values of the noisy pixels which will minimize the summation function, as I've said before. So here is where we call the conjugate gradient method, where we will minimize the summation function by continuously iterating throughout the different values of the detected noisy pixels until we get the minimum value possible for the summation. Okay, so we will get this x over here, which is the modified values for the noisy pixels. All right, and we will substitute those modified values on that part, on the image, on the original image or the noised image, okay, to get the denoised version of that image. So those are kind of like the big parts, okay, of the code. All right, guys, just before I let you go, I want to give you a quick look at the summation and how you can wrap your mind around finding it. If you remember, we have two terms. Each term is a double summation, right? Now, one of the summations is to make sure that you include every noisy pixel. So for each noisy pixel. So this 4 over here, external 4, is for each noisy pixel. This is one of the two summations. The other summation that's within the summation is for each neighbor of each noisy pixel. So how do we create the second summation? Is by going and checking for every neighbor for that particular noisy pixel which we're working on. Okay, so this code goes on each neighbor of every noisy pixel that we're working on within the bigger for loop over here. Okay, so yeah, so for example, in this case, we're working for I plus 1j, and then I plus 1j plus 1, and then I minus 1j, and then you know how to find the neighbor of a noisy pixel, right? Okay, you know, j plus 1i, j minus 1i, and so on and so forth. And I've also included the corners. Okay, it does not really harm to do that. All right. All right. Okay, one last thing before I let you go is that, you know, if you remember, we have two summations. This scenario is whenever the neighbor is within the noisy pixel, and this scenario is whenever the neighbor is not within the noisy pixel. So you should check for that. So over here we have this if statement. If the neighboring point is not within the noisy pixel, then we add it to the, you know, the left term. If the neighbor is within the noisy set, then we add it to the other term over here. And remember something, that if the neighbor is not, or sorry, okay, is within the noisy set, then it's also a variable. Okay, it's not a constant that you take from the noisy original image. It's a variable, and it is changing as you iterate throughout the conjugate gradient method. So if you substitute just the original value of the noisy pixel, okay, in this situation, the algorithm is not going to work properly. So you should remember to make it a variable. Okay, so it should be changing as you are iterating throughout the minimization process. All right, guys, I think that's quite enough. This similar calculations happens for the numerical gradient method. I know I've gone a little bit too deep into the coding. It's just for the documentation process and for whoever wants to, create this algorithm on his own. Thank you so much for watching, and see you in the next one.